Welcome everyone. So apologies for the delay. I mean, there was some issue with the upgrade of Zoom on our system. So it's my pleasure to welcome Manjunath Gandhi, who will be talking about Koopman. Can you just come back to the title?
Sorry.
Yeah, universal set of observables for the Koopman operator through causal embedding. Yeah, thank you.
Yes. Good afternoon and good morning, wherever you are. So thank you, Gandhi, for the opportunity, and thank you, Professor Taylor, for suggesting me to do this talk. All right. So the talk is about, as you see the title, it's universal set of observables for the Koopman operator. So the talk is less about the Koopman operator. I haven't fallen into the trap of the Koopmania, as I call, as yet. I'm sticking my neck out, and the talk is more about the causal embedding stuff. So I don't do a spectral theory of Koopman operators. So this is about learning the Koopman operators without, like any approximations. So learning the Koopman operator on a set of observables. Anyway, so let me begin. Okay. So before that, because this is a joint work with Adrian D. Clark, and Adrian D. Clark was supported from NRF South Africa, so he's just a research assistant, but he has been very aggressively pursuing all the work with me, and helpful comments from Habiteva, Max Haas, and Igor Mezic. Right, thank you. Okay. So getting mathematical models from repeated measurements from experimental science is, of course, now engraved in modern science. Obtaining models from time series dates back to at least 1920s, where sunspot cycles were actually modeled through linear systems. A major breakthrough came through in 1980s with the Tarkin-Steele embedding. Now, currently, the trend is for machine learning algorithms and data-driven approaches through Koopman's theory, and machine learning algorithms like echo-state networks have outperformed Tarkin-Steele embedding. So I'm sure there are other machine learning algorithms which have outperformed, but I'm concentrating on these two. Long-term consistency is a big issue, and I hope the talk would help me to illustrate that mathematical results can guide for better accuracy and also long-term consistency. So the methodologies that I discuss: Tarkin-Steele embedding, of course, and data-driven methods using the Koopman operator in the echo-state network. So methods I do not consider are the kernel methods, for instance, the reproducing kernel Hilbert spaces, and the statistical learning methods. It's not that these are not important, it's because that I do not know enough to talk about these. Okay. So dynamical systems or a dynamical system in this talk would be a tuple where I have a space U, and T is a self-map which is acting on U, and I assume that T is surjective. So if it's not surjective, we can consider an invariant set on which T is surjective, and we can restrict ourselves to that place. And I don't assume that T to be continuous. Okay. So the dynamics is, of course, generated according to this rule. So by repeated iterations, we have dynamics. So where do such dynamical systems arise? Of course, by time T maps of flows of autonomous differential equations. And for numerical approximations of ODEs, we also end up with some maps if the step size is constant. And then the maps are dynamical systems in their own right. Okay, they are discrete dynamical systems. They have their own rich theory. Okay. Something basic again. I'm going to look at two dynamical systems and talk about their equivalence. So suppose there exists a homeomorphism from U to V such that this diagram on the right commutes. Then we say that the system at the bottom and the system at the top are equivalent in the sense they are topologically conjugate. So when we have a topological conjugacy, all the entities like the chain recurrent set, the periodic points, the invariant sets, all of them are transported from one dynamical system to the other. Okay, so it's equivalent to saying that these two are equivalent. So I'll give a picture illustration of this one in the next slide. So if phi is continuous, we say the system is topologically semi-conjugate. So which one is semi-conjugate is important. I say this one at the bottom is semi-conjugate to the one at the top. So in that common terminology in the dynamical systems literature is we say Vs is a factor. That is, the system at the bottom is a factor of the system at the top. Or in other words, the system on the top is an extension of the system at the bottom. Okay. So here are two maps which describe two dynamical systems. One is the full tent map, whose graph is illustrated in black. And then this is the logistic map, whose graph is in the red. So the green lights correspond to the graphs of the identity maps. So say if I were to choose an initial condition 0.4 for the tent map, this has a slope 2. And we know that 0.4 is mapped to 0.8. However, we could instead go map this 0.4 through the conjugacy. Okay, here the conjugacy is this one. So sorry, the phi of x is the homeomorphism. So this maps to a certain point in between 0.2 and 0.4. And once I'm there, we can again compute what is the value. So I've taken an x, hit it with the conjugacy of p or phi, and then computing s. And then I could go back phi inverse. So when I go back, so this is the phi inverse part of it. So this is the phi inverse part of it. And then you see that we get back to the same point, 0.8. Okay, so why am I dealing with this, even though it's a basic thing? Well, all throughout, we are trying to get topological conjugacy. And in all fairness, I should make it amply clear what it means. Okay, so what is a learning problem in the context of this talk? So given data, say U0 from UM, the task is to forecast the successive steps or the successive data points, UM+1, UM+2, and so on, assuming that UN is generated through T. Okay, so that is the updated question. And of course, since there is learning, so what do we learn? We also learn the function T if possible, and because T is the unknown map. So a more involved learning problem is if I have an underlying dynamical system which is unknown, but we are given observations from that dynamical system, and the task is to predict the observations. Okay, I also use the jargon of functional complexity loosely. So for a function which is on the left, which is wiggly, I say that the functional complexity is large. So this is a qualitative statement, not a quantitative statement. It's a loose statement rather. So on the right, I have very simple functions. One is linear at the bottom, and the other one is pretty smooth. So these functions have lower functional complexity. So why am I talking about functional complexity? It is to learn maps which are less functionally complex. So I would like to learn a function which looks like this rather than a function which looks like that. Okay. All right. So let me get to the idea of Causal embedding first through a picture, and then I'll make the statement formal. So suppose I have a dynamical system. So the space is U, and then I have, then I also assume that the map is invertible in this case. So I could get back T inverse of U, T inverse of TU, and so on. And now, if I make observations from this dynamical system, so what are observations? Well, I just take these points and map it onto the real line. So I get a time series. And if I construct what is called as a delay coordinate map of which contains all the past values, not all, but a few of the past values, say if I want to construct the value of the delay coordinate map at U, then I look back here at two different coordinates, but you could go back to any finite number of observations in the past if required. Okay. So what does Takens delay embedding theorem essentially tell you is, although there is no mapping between theta of U and the next observed value theta of T of U, if you construct the delay coordinate mapping, then and if I say this little structure U maps onto some structure here in R3, then we could learn a map F subscript theta on the image of U under the delay coordinate map. Okay, so in principle, this holds for sufficiently smooth dynamical systems T, and if they are diffeomorphic, and U is also a nice manifold. And of course, the delay is large enough. Okay, so I'll get to the formal statement, but before that, I want to make a remark. So one practical issue with learning F theta is, suppose there is an initial condition, or suppose you're kicked out because of observational noise or computational error outside this image of U under the delay coordinate map. Say if the initial condition here is here, we could actually veer off into a separate trajectory, in which case we do not know what happens to F theta tilde, which is the learned map. Okay, so when we learn a map F theta, we just don't learn it on the manifold. You implement any machine learning algorithm or a neural network. So you permit inputs outside the image of the delay coordinate map, and this could veer off, and it could lead to instabilities. So that's the Takens embedding theorem, which Takens proved in 1981. So the important thing is here, the two systems are equivalent in the sense they are topologically conjugate. Okay. So there have been recent extensions to driven dynamical systems, one which is not very recent, but very interesting by Stark. So this is, he considers driven dynamical systems, which I will talk about later in this talk. And the more recent one is on homeomorphisms on compact spaces. Okay. So the difficulty about, the other difficulty about Takens embedding is that the stability of embedding depends on the observation theta. So normally when we make experiments numerically, we look at one coordinate and we try to reconstruct, and that somewhat works fairly. But in general, if you have a very complex observation, then it doesn't work well because the stability of the embedding. So what I mean by the stability of the embedding is, so no doubt we embed U inside a high dimensional space here, R3 in this case, but we do not know what is embedded is actually an attractor for the map for F theta tilde. Okay, so that causes a lot of errors. So there's, I mean, of course, there are adaptations where you do some ad hoc techniques to get back to the trajectory. But, well, machine learning algorithms like the echo-state networks and the Koopman's operator-based methods all work much more better, and they also include more general dynamical systems. So hence, the motivation to go into mapping data into another space through other observables, if I were to say. Okay, So what was an observable? Here, this delay coordinate map, this theta is an observable, and similar in that spirit, we can choose observables and construct different kind of maps. Okay, so let me motivate the example of mapping data into another space through an example where it's static data. So here we have data from two sources, one which is plotted in green, the other one is in red. And this is how the points distribute in R2. So if I take a map phi, and then which is as simple as that, so all these things get linearly aligned. So that's static data, and it's something like magic, because we have what was not linearly classifiable on the left is now linearly classifiable on the right. Okay, so what happens in dynamical systems? Well, we generally don't have any general theory for that. So let's look at the definition of the Koopman operator, which also maps data from dynamical systems from one domain to the other domain. Okay, so given a dynamical system UT, consider a vector space V of observables F. So F belongs to V, and the domain of F is U. Okay, so the operator K, which is the calligraphic K, which I will just refer as K. My apologies. So I've reserved U for the dynamical in the input space of a dynamical system, whereas U is the standard notation for the Koopman operator because it's unitary. However, in control theory, U is also used for the input space, so please forgive me for that. So I'll retain the phase space notation as U, okay, and the Koopman operator notation with the K. Okay, so the operator K, which is defined by, so K acting on F is nothing but F composition T, is called the Koopman operator of the dynamical system or the map T. Okay, so does it always, is this operator well defined? Yes, simply it's well defined because F is just an observable that you're picking. Okay, so if what do we do with the Koopman operator? Well, if one knows the Koopman operator, then we can hit K with to F and then get what happens to the next observed value, F of T of X. So F is an observable. So similarly, if I hit K with F composition T and then evaluate what happens at X, so we get the observed value in the next time step and so on. So we could forecast the time series, that is the observed time series, if I were to call. Okay, assuming that F is a real valued observable, I get a time series. So often V is a Banach space or a Hilbert space. Now, how do we get the Koopman operator? Because the Koopman operator is defined on the space of observables. Well, it's not easy. Even if you know what the dynamical system T is, it's not easy to find the action of the Koopman operator. So in this case, we resort to techniques such as finding what are called as eigenvalues and eigenvectors. So a complex number, lambda, okay, and an eigenfunction, which is also an observable, is called an eigenvalue and an eigenfunction, respectively, if the following relation holds. So the action of K on phi is just nothing but multiplying the observable phi by lambda. Okay, so what happens in this case? In this case, the following diagram commutes. So when it commutes, so what happens is the system at the bottom is topologically semi-conjugate to the one at the top. However, the semi-conjugacy is a very coarse-grained description in this case, because we are just picking one linear, this is a linear transformation. So if I had a nonlinear map, you're making a very trivial linear approximation to the system on the top. Okay, so what do? We try to get more eigenvalues and eigenfunctions. But in general, getting eigenfunctions is not trivial, especially in this diagram. If I were to just pick phi to be a constant, it happens to be an eigenfunction. So we want a non-constant eigenfunction. So finding non-constant eigenfunctions, even if t is known, is hard. So what do? We go for data-driven approaches. All right, for example, oops. So this is the extended DMD algorithm. There are other algorithms. I'm just quoting one of them. So a collection of observables, say F1 to F1, Fn rather, are handled together to get the eigenvalues and eigenfunctions of the Koopman operator. In fact, you can even learn the action of the Koopman operator on these observables by approximating it by a linear transformation. Okay. So when does this happen? Well, if the collection of observables is chosen such that its linear span S, so this, which is what this is the linear span of these set of observables. If it's invariant under the Koopman operator and V is a Hilbert space, then one can find a linear approximation L to the Koopman operator by projecting. So this is an orthogonal projection onto S. Okay, so what do we gain by this? Well, we can determine a matrix A that is guaranteed to capture a few eigenvalues of the Koopman operator. So basically, you are refining your coarse grain approximation. So with one eigenvalue, you couldn't have much, but with more number of eigenvalues, you can actually construct a more bigger or a better approximation. The issue with this is we do not know how to choose observables so that the Koopman operator leaves these span S invariant. So if we had a stray observable without much thought, we could lose this invariance. On the other hand, if you have very few observables, you capture very less of the dynamics. So your coarse grain approximation becomes worse. So that's the issue. Well, the interesting point, of course, A is derived only through data. Okay, so I'm not going to discuss how we derive A through data because there have been talks in the same SIG before. Okay, so I would like to tell what is the main issue for using this approach. So for complex systems, the Koopman operators tend to have significantly more complicated spectral properties. So in particular, you could have non-isolated eigenvalues or continuous spectra, all of which hinder the performance of the linear approximation. So what happens in this case? So the moment I have a linear approximation and my T is non-linear, there's no way if F were to be assuming that F is well behaved, there is no way that you could have a linear map and this diagram could commute. So even if you assumed that S is invariant under K, this is a question mark as well, because I don't see any results. Maybe it is partially true, but then so when I say partially true, it's true in some special cases, because we have to demand the right amount of observables under. We want the observables to be continuous for the conjugacy to carry on, or the semi-conjugacy to carry on. Okay, so there are new algorithms which are called as sparse identification of nonlinear dynamical systems, which is also called a SINDy. It's an algorithm. This was due to two beautiful papers in 2016 and 2019. They overcome the difficulty with linear approximations. So they also go beyond this. So they give a very simple model with very few functions, and that's why the word sparse comes there. So what they do is they construct a library of possible governing equations, which is, of course, is predetermined. So an optimal linear combination of elements in this library is determined to approximate the vector field of the unknown dynamical system. See, the advantage of this is we have physically tractable models, so with reduced number of variables, but there are also disadvantages. The disadvantages is the knowledge of the library needs to know some physics behind the model. And also, time derivatives are calculated, and hence the sampling rate needs to be much higher because of the need for time derivatives, yeah, as I mentioned. Okay, so sampling rate is a critical factor. So really we get very well sampled data from differential equations. So anyway, so Igor Mezic in his talk in the symposium in the field symposium last year, and also in his preprint, mentioned about the idea of learning the action of Koopman operator on a finite set of observables so that we can complete the commutativity in this diagram. So we want this diagram to commute so that what we learn is actually somehow related to the one at the top precisely, and also, you know, we have some guarantee that what we actually forecast is actually correct. Okay, so when this diagram commutes, so Mezic calls the conjugacy, that is the F, and also the map G as a finite faithful representation, assuming that we have a finite number of observables. Now, this is a challenge. So all throughout the Koopman theory, we had finite number of observables, and then we approximated the action of T through a different map. Now we want to have to produce a G. So, well, we want to learn G through data. Okay. First of all, the challenge is we do not know if these observables actually present a learnable map G. So hence the task is unsolved, but we could do this with something different, that is through driven dynamical systems. Okay. So my objective is to find this F and G, okay, for a dynamical system. Right. So here is the theory of driven dynamical systems. And it's a short introduction. So what is that we are going to do? So we're not going to map sample-wise, that is, we're not going to take a single point in U and map to a different space. So what we try to do is we want to map the temporal data, that is the entire history of the temporal data, into a new space. So it looks very ambitious and tedious to collect. I mean, of course, it looks ambitious, but we don't do it at once because it's tedious to collect the temporal data and then decide on a transform to map it onto a different space. So what we do is we use driven dynamical systems. Okay. So what is a driven dynamical system? It comprises of three entities: a continuous mapping, G, an input space, U, which I assume to be a compact metric space. There are relaxations. You could make this work on a non-compact space as well, but well, that is, I mean, for the theory here, it's required. So X is referred to as the state space, and it's also a compact metric space. And the dynamics generated is through these update equation. So as you see here, this is the input at time n. This is the state at time xn. And the state is updated to the next value, x subscript n plus 1, through the map G. Okay, so G is interacting on both of these G can interact in both of these to produce the next state. So this is an example of a non-autonomous dynamical system where we have UN can be considered as a perturbation or an input or a drive at each time step. Okay, now with this setting, I just want to make sure that I stress that G is a continuous mapping. And also I would refer to the driven system as G, assuming that U and X, which are already, I mean, they are already silently assumed. Okay, U and X are always behind. So when I say a driven system G, it means that there is an underlying input space U and a state space X. Okay, so a sequence yn, so this is a bi-infinite sequence. If it satisfies the update equation for all n, then we call that as a solution. So it's also known as an entire solution in the non-autonomous dynamical systems history. Okay, so now may beg a question whether or what kind of animals are these, these sequences. Well, it's important to note that this is valid for all integers. So if you start at certain time, say at time 0, and you plug in an initial condition and an input, the sequence that you evaluate through this update equation is not necessarily a solution unless you can go back in time as well. So these sequences are important, and they could reflect important features of the input. Okay, so that's about entire solutions. Next, so throughout I'm going to use product spaces, and they're always equipped with the product topology. Okay, so does mapping data through driven dynamical systems always unfold the data? Just like what we had in that example with the static data, there's no general theory. But we have a lot of empirical evidence that things actually are much better after you transform. Okay, so I will illustrate that empirical evidence. So the grass is greener on the other side. So what is the rest of the talk focusing on? It's about establishing a theoretical relationship between the temporal input UN and the solution Xn in the state space X. Okay, so my first definition for driven dynamical systems, or driven systems. So I define a subset of the state space called the reachable set, X subscript U. So U is to indicate that as the input space changes, the reachable set also changes. So it's the union of all the elements of all the solutions. Okay, so when I say all solutions, consider all possible inputs, then to note down all possible solutions, and then if you take all possible solutions, then XU, then you take the union of them, and that is your reachable set. So this is going to be a non-empty set. When X is compact, we can always show that we always have solutions, and hence this XU is well defined. So let's look at a very simple example. So I have my input space U, which is the set of real numbers between 0 and 1, and X is also the same. And I have this map GU of X, which is UX by 2. Now, regardless of what happens as for the input, that is, regardless of whatever sequence I pick inside U and feed it into my driven system G, the only possible entire solution is where Xn is identically equal to 0. So for this example, the reachable set is just a single element. So I hope this gives a clear idea of what is an entire solution as well, because if you choose an initial condition other than 0, then you still get forward iterations under the update equation of G, but there is only one entire solution that's which is valid for all time. Okay, so this reachable set is, I'm looking at the reachable set because I want to relate the input, that is the temporal variation in the input, to the reachable set. But this is too small. Okay, so we can actually define a class of driven systems so that we avoid these kind of trivialities. So I introduce a notion called state input invertibility. So we want the reachable set of the driven system to be large enough to relate to the input. So that's the objective. So I say the driven system is SI invertible if I fix X and then the map that I get from U to X, if that is invertible for all X. Well, what are examples for this system? We'll come to that a little later, but I just want to give, just want to remark that the recurrent neural networks or the echo-state networks that are being employed do not satisfy this property automatically. So we need to make some amends. All right. So what is the understanding? I can define SI invertibility alternatively. So what does it mean? It means that if I take a solution for the system, so this has got nothing to do with any property of G. So this is just we are looking at solutions. So if I look at 2 points, successive points in a solution, then these 2 successive points would determine the input at the previous point. So if that holds, then we can say that G is state input invertible or simply SI invertible. Okay. Now I want to establish a relationship between the temporal variation in UN and the solution Xn. In general, so the solution lies inside the reachable set. So I want to establish a relationship between the input and the solution. So in general, we may not be able to establish a relationship since the interaction of G with the inputs may be complex. So what do I mean by this? Specifically, these maps, family of maps that I get as a very end, this could give rise to complexity of the dynamics. So to illustrate this, let me look at a simple example. So I look at a driven system. I feed a sequence UN, which is a sinusoidal signal, into the system. And then I look at the response of the system. So the response of the system is in red for the parameter, for the first parameter, that is with parameter being equal to A. And for the parameter B, so the response is kind of aggressive, although there is some kind of sinusoidal envelope. So the solution keeps jumping too rapidly in comparison to the first response, which is in red. So the response in the red assumes some kind of properties on G so that it's reflecting the input faithfully. So what is that property? Well, before I come to that, I want to address what really happens, like in terms of complexity between the input and the response. Okay, so I want to abstract the complexity, between the abstract, what is G doing rather. So in other words, I want to say abstraction of saying GUN does not add additional complexity into the solution at each time step. So what do I mean by this? So I have a left infinite input, okay? And I denote U with the left arrow on the top to be the space of all left infinite sequences contained in U. And now so this is being fed to the system. So the left infinite input is fed to the system and a new input arrives, okay? So this I can denote symbolically by appending V on the extreme right. Okay, so this operation I can define through a mapping, sigma V, which is, it acts on U and appends the symbol V onto the extreme right. So that's your new input at time, say at any time, let's say time N. Okay, now I want G not to introduce any new additional complexity. So what does it mean? It means that I want this diagram to commute. Okay, so what does this mean? So sigma v comes in. So this is so you have a sequence, left infinite sequence. A new input v comes in. So you're mapped to a new value, which is this value there. And I want a continuous surjective map H such that H takes this to the reachable set, and it is just, this diagram commutes. If this diagram commutes, then we introduce no new additional complexity into the dynamics. So if I go back to this previous diagram, if the diagram commutes, so I will not have this new jump up and down. So mind you, I want this map H should be such that it's valid for every left infinite sequence contained in this space U. Okay. So when such a map exists, we call H a universal semi-conjugacy. All right. So when do we have a universal semi-conjugacy? So that gets me to a property of G. Okay. So let me read the theorem. So let G be a driven system. So I assume silently that the input space is compact and the state space is also compact. Then G induces a universal semi-conjugacy if and only if G has the unique solution property. So this unique solution property is familiar. So I'll come to that. All it means is for every input UN, there exists exactly one entire solution. Okay, so that's a question mark as to when it exists and things. That's a question mark, but that's exactly equivalent to the echo-state property in the machine learning literature. So I would prefer to call this as unique solution property because there are other variants of this echo-state property definition. So one is an echo-state input readout relationship. So where you also have a unique solution in the readout. So I want to, this doesn't mean that. And also there is the notion of echo-state property with respect to an input, which I don't consider. So this is, I want this to hold for every possible input sequence inside U. So for every input sequence, I should get exactly one entire solution. It does not mean that this entire solution as yet is actually uniquely related to the input. Okay, so you could have H could be in principle, could be a a non-injective map. Okay, right. So I don't want to forget my objective. My objective is to learn a function. Okay, so I want to learn a function from XU to XU because I want this diagram to commute to get to the finite faithful representation in the Koopman's theory. Now, this is not possible in general. So we need to make some changes. So what are those changes? All right. So we define a relation on the reachable set. So what is a relation? It's a subset defined on XU cross XU. So what is that relation? That relation is simply the collection of adjacent points on your solutions. And that YT, I call that as YT because I want to restrict the inputs to be coming from a dynamical system. So why am I restricting inputs coming from a dynamical system? I want to get a learnable map here, and I can't do this for any sequence that comes here. So I want to take a subspace out of this one. So for that, towards that, I actually restrict my inputs to be orbits coming from a dynamical system. So T could be discontinuous, as I told before. Okay, so I define a relation. Now this relation has got nothing to do with the echo-state property that I defined or the unique solution property that I defined in the previous slide. So this is totally independent. So I'm furthering my question that I had 2 slides ago. So I had this universal semi-conjugacy notion, and I want to relate, a map here to a map there. So for that, I want to define a relation. So this relation consists of all tuples that you obtain for the driven system. Okay, so that's also symbolically indicated, schematically indicated rather here. Okay, so we look at 2 adjacent points in a solution and determine that as a single point in the space Y subscript T. And where is Y subscript T? It is in the product space of XU with itself. Okay. Now I can define a map on YT. So this is regardless of whether for any given driven system, I can define a map on YT. Okay, so this is a theorem, which is simple to prove as well. So let G be SI invertible. Okay, so that's why I'm using this, notion of state input invertibility. So just to recall what it is, if I have 2 successive points in a solution, then I can determine what was the input that led to me there. Okay, so input value rather. All right, so let G be SI invertible and let UT be a dynamical system. Then we have a well-defined map GT on this relation. Okay, and that relation is just updating this to the next 2 successive points. So xn minus 1, so this map GT rather is mapping xn minus 1, xn into xn and xn plus 1. Okay, right. So I want to give a name for the dynamical system that we get. I simply call that as if UT is a dynamical system, I want to call this YTGT is the dynamical system induced by G. Okay, so this is a new dynamical system that we have in the space of the driven states. Okay, so can we obtain a relationship between the original dynamical system and this one? Okay, the answer is indirectly yes, but it's not possible always. So I need a new notion, that is the notion of an inverse limit system. It is new in the sense for the machine learning fraternity, but not for the dynamical systems fraternity. So it's a classical notion as well. So what is an inverse limit space for dynamical system? Well, I'm going to look at all left infinite orbits, starting from left infinite orbits of the map T, and I give that a new name. Okay, so this is UT with a hat on the top. So this space is the space of left infinite orbits. Mind you, I can define the left infinite orbits because I assume T to be surjective. Okay, so what we have is this one is going to be a subspace of this product space U with the left arrow. Okay, so it's in fact a very small subspace because this U could be an infinite dimensional manifold if U were to be a manifold, and this one to be just a finite dimensional manifold. Okay, so just to get an idea of what this inverse limit space is, so if I have one U minus 1, so if I pick a U minus 1 inside U, then for this map here, I have 2 pre-images. So for each one of these 2 pre-images, the second so the second element inside this inverse limit space, we get 2 different, 2 different points in that inverse limit space. So in general, as you go further backwards, you get, for a non-invertible map, you get plenty of new elements in as the left infinite orbits. Okay. Now on this inverse limit space, we can define a self map, which is T hat. And that is simply given by the following, that You just take the last value and hit it with the map T, and this is your new element inside the inverse limit space. So this mapping is related to the mapping T, because by the following fact, when T is a homeomorphism, then T hat and T are conjugate. Otherwise, the inverse limit system. So this map on T hat, on the inverse limit space, which is given by T hat, is called as an inverse limit system, and that is actually has something more than T because of all the left infinite orbits. So we say T, when T is just not invertible, then T is in general is just a factor of this inverse limit space or the inverse limit system. So the point to take from this slide is I have an inverse limit space and I have a T hat. So this together actually contribute to what is called as an inverse limit space. Now on your input space, so the left infinite input space, it could host a lot of, inverse limit spaces. So for each dynamical system, I could have, an inverse limit space of its own. All right. Okay, and all these are contained in the left infinite product space U. Okay, so what do we do with this inverse limit space? Okay, here is the theorem. I call this as a causal embedding theorem. So let G be a driven system that is SI invertible and has the unique solution property. Okay, let H denote the universal semi-conjugacy, and I define a new mapping H subscript 2, which is very easy to define. So R is the right shift on the left infinite sequence U. So what I have here is for U, 2 successive points of the solution. Okay, so H2 is just taking the 2 successive points on the solution and 2 specific points. So that is simply got by, say, if this was the input up to time n, so this would be the solution value at time n, this would be the solution value at xn minus 1. Okay, now the function H2 embeds the inverse limit system. So it's going to embed all of this. So it's going to, this is a topological embedding. So it's going to map this into the subspace such that H2 restricted to its image becomes a homeomorphism. Okay, now there's something more. Okay, so if once the embedding takes place, then what happens is this dynamical system that I defined on the relation y subscript t, okay, so or else which I called as the induced dynamical system, that becomes a factor of this system on the top. Okay, so this dynamical system is a coarse-grained representation of what is at the top. Now, when can I have a complete representation? That is, when can I have the 2 systems conjugate? Well, if when T is a homeomorphism, then these 2 things become conjugate. Okay. Now, with this conjugacy diagram, I can't wait for too long to tell you that if K denotes the Koopman operator for the inverse limit dynamical system, so this is the inverse limit system of the given dynamical system, then this is a finite dimensional faithful representation of this one. Okay, so what is this inverse limit system? Well, this inverse limit system is actually topologically conjugate to the original system when T is a homeomorphism. Otherwise, it's still an extension. So it contains all the information of the original system, UT. Okay, so observables for the Koopman operator for the inverse limit space. All right. So let me make this much more clearer, because this could be an abstract space. But for practical purposes, we could land up with X inside the Euclidean space. Okay, so this may look abstract because UT hat, I need to tell that it includes some kind of functions. So what are those functions? Not UT hat. This map H2 includes some kind of functions. These are nothing but the component or the coordinate functions of H2. So each one of them maps to R2. Okay, so my map GT is actually acting on Rn cross, it's acting on a subspace of Rn cross Rn. Okay, and I have observations which are just the coordinate functions of this function H2. All right, so this together form a finite dimensional representation. And what is the action of the Koopman operator? The action of the Koopman operator is nothing but K acting on one of these components is nothing but this relation here, where pi I is simply coordinate projection. So H2 is acting on Rn cross Rn into Rn cross Rn. GT, H2 is acting on the inverse limit space, brings me to Rn cross Rn. GT acts on Rn cross Rn, and pi I is just the projection, okay, into the coordinate. So that's the Koopman operator acting on Fi for us. All right, so what can we say something about the spectrum? Well, the spectrum of the Koopman operator of conjugate systems are identical. Why are they identical? Well, we know when they are conjugate, the entire spectrum just carries over. Okay, and well, the spectrum of the Koopman operator of a factor is contained in its extension. So when we have an invertible system, a non-invertible system, then the inverse limit space is just an extension of the original one, but doesn't matter. Still, the new system that we define here contains all the spectrum of that, but it could contain additional elements which we don't desire in the spectrum. Okay. Now, essentially, this map H2 defines, this map GT defines a one delay lag dynamics. So if people are familiar with ecostate networks, it determines the dynamics between two successive reservoir states. Okay. Right. So our grand idea was to obtain, map the dynamics from one space to the other and get a new map, GT, which is of course learnable through the data that is fed into the driven system. But then the question comes whether it lowers the functional complexity. Okay, that's the whole objective. So why do I map data from one space to the other without gaining advantages? Okay, so I want to introduce a measure. Okay, so we know the Pearson correlation coefficient for one-dimensional random variables. In the multi-dimensional case, it has a straightforward extension, which is computed through the correlation matrices sigma, which is defined here. So if you take the appropriate traces, then we can define a number rho. So this rho tells us the following. So this is, you can find a lot of references. I just quoted one. So what does this rho indicate? Well, if y is related to x through a linear relationship. So what is that linear relationship? Well, A is a matrix, acts on X, and then there is, this is an affine transformation. So if it's related in this way, rho is equal to plus or minus 1, and the converse is also true. Okay, so now we can alter the functional complexity of GT by increasing the dimension of X. Okay. So we are mapping your inverse limit space into another inverse limit space into another space, which could be an Euclidean space. So I could talk about the dimension. And then if this were to be an implementation with a recurrent neural network, it's just simply by changing the number of neurons, I could alter the functional complexity. Okay. So I use RNN, which is of this kind, which is given here. And this is one of the standard, from prototypes of a recurrent neural network. It could work. I could have used something else as well. Okay, so A and B are unknown. A and alpha are real parameters. A and B, the capital A and B are matrices, which take you from the input space into the state space. All right. Okay, so here is some evidence on the reduced functional complexity, which we measure through this multidimensional correlation coefficient rho. So in the case of a Lorentz map, this is the correlation that we have. And then what we have in the reservoir or in the new state space, which is in YT, is just a small improvement. But there comes a dramatical improvement when we actually feed an observation of the original system. So what is in the second column is the number of nodes in the network. So if I increase the nodes, then I also see that I actually gain more linear relationship between the two points which are given as these two vectors here. Okay, so with the logistic map, it's quite drastic. So if I have an observable, and then if I have, that's the linear relationship measure, rho, and that's the rho value when we actually transform it into the other side. So from this picture, it looks like the grass is greener on the other side. So we could actually try to learn a map on the reservoir. Okay, all right. So the map GT, so in principle, by feeding the dynamical, so the driven system by a left infinite input, I can learn a map GT. Now, this learning the map GT, you could use any machine learning algorithm in principle, but there are some advantages if I don't learn this map GT the way it is, but by learning a very simpler map. So we could save a lot of resources. So what is that that we want to learn? So this is a straightforward thing to show. So existence of G subscript T also implies the existence of a map between the two inputs, the two values of this reservoir, xn and xn minus 1. So these are values on a solution. And the map gamma takes this value to the next input value un. So un has not been presented to the network as yet. So what has been presented to the network is up to u subscript n minus 1, and you learn this map gamma. Okay, so that's when we do this. So this was the original setup where we learn GT as it is. So I have an input, and then this causal embedding, that is H2, takes me to successive values on a solution. And there is a map GT. Now, instead of learning GT, we learn a map which is something different. So that map gamma takes me to the two values, takes the two values into the next input value UK. And this pi2 is nothing but a coordinate projection. So as you see here, take these two values and I learn UK. Pi2 acts on the second coordinate here and brings it down there. So that's a coordinate projection. Now this is then fed, can be fed into the driven system. We have G with us, and I can get the next value. So why do we do this? So the implementation is actually in the red, although there is the mathematical theory is like, which is printed in black. Well, there are a lot of advantages of doing this, and I will tell you those advantages. So before that, assuming this map gamma exists, So let me get to these two equations. So that's the equation which represents the commutativity here. So if I look at the first equation, so this is UK plus 1. So that's the prediction that you're doing. And UK is the previous step. So we have derived a non-linear, perhaps, difference equation here, because xk is depends upon the previous values of the input. So xk was nothing but the value of the universal semi-conjugacy, and the universal semi-conjugacy depended on the entire left infinite sequence. Okay, so in this case, so what happens is the first equation is a nonlinear difference equation, and the second one is an equation with an auxiliary variable, right? So we introduce in practice plenty of coordinates for the auxiliary variable. So these are equations which are exact. So when I say exact, if you don't learn gamma if you learn gamma rather without error, and your UK is noise free, and from an invertible system, these equations are exact. So we had those equations from the SINDy algorithm. So they also produce equations. The difference here from there is we have a lot of complexity into the system because we have a lot of auxiliary variables, but we have exact equations, and we don't need to know the physics behind the model to determine what kind of library of functions that I need to choose for determining my equation. Okay. Now, I said that implementing through the red, rather learning a map gamma, because, learning the map gamma is much more easier than learning the map GT, because the dimension is much smaller usually. So the input is of a much smaller dimension. All right. Now, what do we do with the second one? So the second one is the driven system. So I can feed it, I know what is G, I can feed it back into the driven system to get this one. So here comes a big advantage. So we do this, the driven system has some very special properties. So what are those properties? Well, one is called as the uniform attraction property. So in practice, we don't have the entire left infinite sequence, but a finite segment from the past history. And when we feed a finite segment, so in some sense, the sequence that you get by starting with an initial condition y0 actually approximates the actual solution fairly quickly. And we can actually get an uniform bound on how quickly it approximates. So that is actually described by this uniform attraction property. So for lack of time, I will not go through the entire statement. Okay, so that's a very nice handy property. Okay, so just for the non-autonomous dynamical systems fraternity, all of the solutions turn out to be uniform attractors. So earlier they were known to be pullback attractors, but they're all uniform attractors when U is compact. Okay, next, the driven system also enjoys two very nice properties. One is the property which is called, which are called that as input related stability. So what it means is these functions h2 and this h are all continuous. Continuous with what? Continuous with respect to a perturbation. So continuous with respect to the inputs coming from the left infinite space. Okay, so a small perturbation in the past history will actually not destroy your simulation. So if I made a mistake in the input a long time ago, then we see that the reservoir states actually do not actually give too much of importance to the distant past. Okay, that's because we have the product topology. And the next property that I have is the parameter, if I have a parameter lambda, which is not necessarily real, it could be any parameter that defines the driven system G, then if that is continuously related, then the universal semi-conjugacy and the map H2 are also continuous. So for the Koopman operator fraternity, your observables will change by a small factor if you alter the driven system also by a small factor. Okay, we alter the by small parameter rather. Okay, so all these properties make us to implement through this process rather than going by GT. But there is one more. So what was it? So in the Tarkin's delay embedding theorem that I mentioned a while ago, at the beginning rather, so I mentioned that if I choose an initial condition, which is just outside the image of the embedding, then it could veer off completely, into a different new trajectory. But here we have something. So if H2 embeds a dynamical system, which is shown in dark orange here, then what really happens is the saturation function. So I have, we can design G, so in such a way, so there's a function here, tan H sitting there, so that it actually, puts a bound so that your trajectories don't veer off. And also it it gives you a dissipation so that this yellow region becomes an attractor in that system. So why is this important? We could make a certain amount of error when we actually do the computations because of noise. And then an actual trajectory which should have been in this orange space could be kicked off into the yellow space, but then it can't wander off too far away. So in general, if we make this orange space bigger, so this yellow space is actually fixed by the network, or the driven system rather. So if we make this, if we can expand this, then we have better results. And one way of expanding this is we can control that in the recurrent neural network by changing the parameter alpha. Okay, right. So here is a summary of what we did. So for the unique solution property, it enjoys the uniform attraction property. It has input-related stability, parameter-related stability. And the SI invertible systems, they enjoy the following properties. That means that a well-defined map GT comes into the picture. Okay, so at the intersection of these two, we have the causal embedding, which guarantees that this diagram commutes. Okay, so when this diagram commutes, we have an equivalent dynamical system when T is a homeomorphism. Otherwise, this becomes a coarse-grained representation, as I said. Okay, so how do I get SI invertibility from looking at these networks here? So if A and B are matrices of the same dimension and they're invertible, then we can actually do some alteration on U, for instance, append just zeros on U so that it matches with the dimension, and we can get the SI invertibility very easily. Okay, so what that was the theory when we had inputs which were fed directly into the driven system. What if we have observations from the input? Well, all the theory that we developed simply holds. So if I have an input from a delay coordinate map, you could feed the input into the delay coordinate map, and we can show that the whole thing is actually topologically conjugate whenever the Tarkin's embedding holds. So Tarkin's embedding could hold in general. U doesn't need to be a manifold, as I told before. U could be a compact metric space, and T could be just a homeomorphism on that. And if it satisfies some certain conditions, then we actually have this diagram commuting. Well, okay. So with all these modifications, with all these theory, I want to learn the map gamma, as I showed on the slide here. So I want to learn the map gamma here. Okay, so I learned the map gamma through a feed-forward neural network. Well, you may question why use another network when we have the ecostate network principle of using linear regression. Well, it's going to provide you extremely accurate predictions, long-term consistency, and there is no difference for linear regression except that, of course, there could be I do not want to object to some theories, but linear regression is an approximation. Gamma is actually you're learning the actual map that is being presented. Okay, so we need a feed-forward neural network, and we could use a deep learning method, and we could implement by a feed-forward neural network. Okay, so I'll illustrate some numerical results. Before that, I just want to tell you that the input is padded with zeros to match the dimension of A. This is not an approximation, but it's just that you're assuming you are actually embedding the input into a higher dimensional space. That's it. Okay, now the recurrent neural network has 1,000 neurons, and the feed-forward network has this architecture with 12 layers and 64 neurons in each layer. Okay, and the minimum mean square, the mean square error in the L2 norm is minimized. And all of the experiments have added noise, which are either of these two values. Okay, so the noise is normally distributed, and it has a standard deviation of these two values. Right, so before I begin, I just want to tell you, I'm using the same network. So there is no tinkering. So everything has to work according to theory. So I've used recurrent neural network of this kind, but we could use any network which is SI invertible and has the unique solution property to get to this numerical result. So here is the result with the Lorentz system. I use a step size of 0.1. So this step size is 100 times smaller than the step size that is being used in the SINDy algorithm. So 100 times larger, not smaller, larger. So the sampling rate is much smaller. Okay, and I plot 50,000, we have 50,000 samples that are plotted. So Adrian has given some beautiful pictures. So with that, we can reconstruct, so that's the noise SNR. And after discarding 500 samples and with a training length of 2,000, after 50,000 values, it still stays on the attractor. It's not a surprise because the Lorentz system has been dealt very well. But what is the challenge here is the step size is 0.1. Okay, the SINDy algorithm uses a much smaller step size. Okay, next, something which is conjectural at this time. I'm sure Grigorova and Ortega and others, they're working on a Tucken's embedding theorem. So I know a little about it. So when we feed a complicated input, which looks like this. So these are the values of the coordinates of the Lorentz system. And this is an observable, which looks like this. For this observable, we could actually learn the reservoir states. So we're not just feeding the delay coordinates, the projections, but we're feeding a very complicated observables, and we can still recover. So it means that when we project data from one space to the high dimensional space through the right kind of driven system, then we have a construction which is very faithful, like this. Okay, so these are the the time series plots of the actual and the predicted ones. And although we see that there is a difference between the actual and the predicted ones, it's still, the important point is that even after thousands of iterations, we still stay on the attractor. Okay, now I look at another dynamical system, which is the full logistic map, and everybody knows what's the full logistic map. Its graph looks like something what is plotted here. So for this, the echo-state network fails miserably. The linear regression doesn't work. And for this map, this is what we have. All right. Okay, so I want to make another point. The point is, when we learn a dynamical system, it's also important we actually also learn the statistics of the statistical aspects of the dynamical system. In particular, what is called as an invariant density. So invariant density tells how an orbit is actually distributed in the phase space. Okay, it gives, so higher the value of the density, that means the orbit spends much more time in that region. Now, with noise, what you have in red is the actual invariant density, and what you have is the density of this learned map. All right. So the next map that we learn is the Hennen map with intermittency. Now, intermittency is the new thing because most of these machine learning algorithms, they fail, including the eco-state networks. They fail when you have intermittent data. So what is intermittency? That is, you have bus, chaotic bus, and then you have narrow passages where the dynamics must become simpler. So in this case, we also find that we have a good reconstruction. And in addition to that, we also find some denoising effect. That is because of the network that we are using, it averages values from other nodes, and in that process, there is some denoising. So this is the attractor that's original, and that's the attractor that is reconstructed. Okay, the last one, which is actually a challenge. It's called the Premiere Mandelion Map. It's a family of maps. So the map is described by this, and the graph of the map, of course, what is shown is with the noise. It's given there. So this map is incredibly hard to learn, and we could do this with the recurrent conjugate networks, that is the RCNs. Okay, so I have the time series plot, and you see because of these passages where nothing happens, so in that space, the dynamics gets completely, the eco-state network, for instance, doesn't pick up this, and it starts predicting everything like this, everything like a chaotic bust. Okay, so with the RCNs, we could do this. And hence we could also approximate the density of one of these coordinates, which is also plotted in this right-hand bottom corner. Okay, so comparison before I end. Observables in the case of DMD, EDMD, SINDy are chosen or optimized. Here, we always get the optimal observables. Okay, optimal observables in the sense that we have a finite, faithful representation in terms in the language of Igor Mezic. Okay, and these are R2 valued observables. All right. The simplicity of the DMD and the other methods are equations from data have few variables. Here we have plenty of auxiliary variables. So if you want to analyze this dynamical system for some other purpose, then this could be a not so nice factor because we have a lot of auxiliary variables. All right. Equations are not necessarily exact in the case of the DMD and the other data-driven methods, but here we have exact equations in principle as long as the data originates from a homeomorphism. If it's not from a homeomorphism and it's from a general dynamical system, then we have semi-conjugate dynamics. Okay, conclusions. Well, so the first point that I want to tell you is if you do not seek an expression for observables, so all throughout, H2 is determined by the network. So we don't have an expression for that one. Then the driven dynamical system with the causal embedding property gives rise to the right set of observables. So we have lost something, but we have gained something very important. But anyway, it's not important to know what the observables are unless you have some specific applications. Next. Can we construct driven systems so that the map in the induced system is less functionally complex? Well, that's a question. So what I have used is the recurrent neural network. One single network for all systems. There are no approximations. There's no feedback into the network or anything like that. So, but we could perhaps with time be able to learn those class of driven systems which give you very good induced dynamical systems. Next is Herbert Igor in his Scholarpedia article on the eco-state networks says today, as of 2017, with the advent of deep learning, the problems faced by gradient descent based training of recurrent neural networks can be considered solved. the original unique selling point of ESN's stable and simple training algorithms is dissolved. Well, that was his opinion, but we see now that we can combine deep learning along with the ecostate property or the unique solution property to get something much more better than what is trained through recurrent neural networks alone. Right. So, finally, to make a comment, we've used the unique solution property in combination with deep learning to construct high fidelity models for dynamical systems. But there is a cost, and we have sacrificed simplicity in training. But I take refuge under Herbdeger's comment that we could actually sacrifice simplicity because now we have deep learning. All right. So thank you very much for listening to me patiently. And if you have any questions, please let me know. Thank you very much.
Yeah, thank you very much.
My apologies. I've overshot my time. I know I've started a bit late, but
no, it's all right. Yeah, I'm sorry. It's I had also this issue with the Zoom meeting on. Yeah. Questions? Yes, I might see someone raise his hand. Yeah, Juan Pablo, yes.
Manjunath, thanks a lot for your presentation. It was great. Look, I wanted to ask about the specifics of this causal embedding theorem that you showed to us. So this in this U-hat that you have in there, could you give a few more details about who this space is, what the topology is? So, because this UT-hat that you have in here is not the semi-infinite sequence spaces that you were using before when you were talking about these other properties, right? This is something else because according to the example.
The UT-hat is just the left infinite orbits of the dynamical system that you have.
Okay.
So it is a subspace of the product space of U. I mean, this U with the arrow on the top is just the product space of U, left infinite product space. So on this, you have a product topology. And this UT-hat is a subspace of that one.
I see. Okay.
Right.
So then when you give us the example with this big diagram of who talks with whom, there were only two factors. So a bit farther.
Yes, is that the one? This is the conjugacy embedding too. Okay.
And then there was this big diagram. Exactly. So you see.
Yes. So this this map is the map induced by the original map on the inverse limit system or the inverse limit space. So that's T on the T with a hat. So how is the T-hat defined? T-hat is nothing but T acting on the last symbol, U minus 1. So you push the entire sequence to the left, and then you have a new symbol there. So that is the talking. That has nothing to do with the input. Yes.
And in the same, because you see, for tokens you need invertibility, right? It's only for diffeomorphisms. So or for homeomorphisms if you are in the continuous category. So in your case you need also invertibility or not for the dynamical system?
If you want just if you have just happy with semi-conjugacy, T could be any non-invertible map. But if you want exact conjugacy, then we need T to be a homeomorphism.
I see. No, thank you very much. I look forward to reading the paper. By the way, when do you already have it written down? Is it coming or?
Yes.
Because I haven't seen a draft passing, so that doesn't exist yet, right?
Yeah, it was posted on archive just this morning. So you have.
Okay.
Right. There's a map. It doesn't have all the details because I haven't put the supplementary information, but I will send you one copy as soon as it's...
Okay. Thank you again.
Thank you very much. Thank you for the comments.
All right, thank you very much. Other questions? Yeah, all right. That's it seems. Thanks again for the nice talk. And I'm going to just thank you on behalf of everyone else. Thank you.
Thank you very much. Thank you.
Yeah. Is there another question? Or is it Juan Pablo? Do you have like another question or?
I don't see how many are left in the audience, so I don't know.
No, it's I don't see anything here. So
yeah. Okay. All right then. Okay. Take care, everyone. Thank you. Bye bye.
Thank you.
Yeah, nice to see you people. Bye.
Yeah. Bye. Bye. Take care.
Bye.